In this video, we're going to look at how we balance redox reactions because it is often a little bit different from the way that you're used to balancing reactions. Because redox reactions are electron transfer reactions, we need to pay closer attention to the charge. When we balance a reaction, we need to balance both for mass and for charge, that we need to make sure all of our particles are accounted for. And up to this point in your chemistry career, you've only really had to think about the mass, and the charge has just kind of worked itself out on its own. So although you have been balancing for charge, you haven't had to think about it separately. Now, because electrons are moving around independently, you need to think about it. And we have a process for that that's a little bit different. Essentially, what we want to do when we're working with redox reactions is that we can think about the oxidation and reduction processes separately. They have to happen together, but we can think about them individually. And that helps to make this process easier in a lot of cases. It is not always necessary to go through this whole process that I'm going to show you today, but this process will come in handy for more complex redox reactions. So today we're focusing on pretty simple ones just to get the kind of bare bones of this process down. And then in the next video, we'll kind of amp up the complexity a level, but it'll be using the same process, just adding in a couple extra steps to deal with a few weird situations that we may encounter. So when we think about these processes independently, these are known as half reactions. So we can think about the oxidation half reaction and the reduction half reaction as two separate things. Notice we call them half reactions because they can't happen on their own. You need two halves to make a whole reaction. When we balance redox reactions, we can balance the half reactions separately. And then combine them into our overall net reaction, which is essentially what we are doing. And we do this because we need to make sure, this is the easiest way to make sure that we balance for both mass which is our number of atoms of each element, and our charge, which essentially what we're balancing for here is our number of electrons. This is the easiest way, this half reaction method that I'm going to show you is the easiest way to make sure that that happens. So I'm going to do an example walking you through this whole process step by step. So the first thing we need to do to complete the half reaction method is identify what is being oxidized and what is being reduced. And this is what we use our oxidation numbers for. We assign oxidation numbers to all of our atoms in our reactants and products, and then see how those oxidation numbers change between our reactants and products. That will tell us what is being oxidized and what is being reduced. We should find that one element has its oxidation numbers increase, which means that that is being oxidized, and one element has its oxidation number decrease, and that thing is being reduced. So if we look at our elements here, we see that copper, we have a single atom of copper here with a +1 charge, which means its oxidation number must also be +1. On the product side, the charge has become +2, so our oxidation number has become +2 as well. So we can see that our oxidation number is changing from +1 to +2. That is an increase. So that is being oxidized. So in this reaction, copper is being oxidized from copper +1 to copper +2. For the chlorine, we're starting out with an oxidation number of 0 and ending up with an oxidation number of -1. Our oxidation number has decreased by 1, which means that our chlorine has been reduced. So you should always find one thing is oxidized and one thing is reduced. If not, check your oxidation numbers. And from here, we can separate this out into our half reactions. So our half reactions are just what is being oxidized and what does it turn into. So copper 1 becomes copper 2 is one of them. And then what is being reduced and what is it to turn into? So Cl2 to Cl- is our other one. So the first thing we want to do is write our unbalanced half reaction. So exactly what I just said, copper 1 to copper 2 is our oxidation. So we have Cu plus to Cu2 plus. So that is the unbalanced version of our oxidation half reaction. Then our reduction, we have Cl2 to Cl-. And that is the unbalanced version of our reduction half reaction. So the next thing we need to do is just balance for mass by adjusting coefficients. So this is balancing a reaction in the normal way that you have always done. Looking at our oxidation reaction, we have 1 atom of copper on the left, 1 atom of copper on the right. So that one's already fine. We don't need to change anything. In our reduction, we have 2 atoms of chlorine on the right and only 2 atoms of chlorine on the left and only 1 on the right. So that means that we need to put coefficient of 2 in front of that chloride ion on the product side in order for this to be balanced for mass. Then the part that's new to us is balancing the charge by adding electrons. So the total charge is equal on both sides. So the total charge of the reactants needs to be equal to the total charge of the products. And we add electrons in order to balance those out. So currently in our oxidation reaction, we have +1 on the left and +2 on the right. Electrons are negatively charged, so we're always adding electrons to the higher charge side in order to bring that charge down. So in this case, we're going to be adding 1 electron to the right side here, so that +2 plus -1 equals +1. So now the left side and the right side have equal charge. In the reduction reaction, we have 0 charge on the left and -2 on the right. Note that there are 2 of these and each of them has a -1 charge. So that means that we need to add 2 electrons to the left so that we have 2 negative charges over here, 2 negative charges over here. We have balanced the charge on these reactions. So we now have balanced half reactions, which means we can combine them back together to get our net reaction. So there is one thing we need to do before we can combine them. And that is that we need to make sure that the number of electrons we lost in the oxidation is equal to the number of electrons gained in the reduction. Every electron needs a place to go. None of them want to be left lost and alone. So all we need to do is multiply our half reactions by whatever coefficients we need in order to force this to be true. So we have 2 electrons on the left and currently only 1 on the right in our oxidation. To fix that, all we need to do is multiply all of our coefficients here by 2. Note that you do have to multiply all of your coefficients in a half reaction because that's the only way it stays balanced. So just like we did back with like Hess's law when we were multiplying reactions, you multiply all of your coefficients by the same value to keep it balanced. And now we have 2 electrons given up in our oxidation, 2 electrons taken on in our reduction, so every electron has a place to go. So at this point, we're just adding our reactions together and canceling out our electrons. So we have 2 electrons on the left, 2 electrons on the right, and we will be left with everything else here. So we'll have 2 Cu plus Cl2 forms 2 Cu2 plus and 2 Cl minus. So this one is simple enough that if I told you you needed to balance for charge, you could probably just play around with the coefficients for a few minutes and figure out how to balance it without the half reactions. But again, when we get into more complex reactions, the half reaction method is really the only way to do it, and is actually the most efficient way to do it. So this half reaction method seems like it's, a long convoluted way to balance a reaction, but once you get the hang of it, it's really not so bad. So I would like you to pause here for a moment and try this next example. So again, you're gonna try to balance this reaction by first writing and balancing the half reactions and then combining them back together into the net reaction. So pause here and try that on your own. So the first thing we want to do is identify what is being oxidized and what is being reduced by assigning our oxidation numbers. So these are all monatomic things. So our oxidation number is just going to be equal to our charge. So we have zinc going from +2 to 0, which is a reduction since our oxidation number is going down. And we have aluminum going from 0 to +3, which is an oxidation since our oxidation number is increasing. So our reduction half reaction is going to have zinc 2 plus producing zinc solid, and our oxidation half reaction is going to have aluminum forming aluminum 3 plus. So from here, we want to balance our half reactions. Both of these are already balanced for mass. We have 1 atom of zinc on each side. We have 1 atom of aluminum on each side. So all we actually need to do here is balance for charge by adding electrons. So we'll need 2 electrons on the left side of the reduction half reaction, 3 electrons on the right side of the oxidation half reaction in order to balance these. Note that you should always find electrons on the left in a reduction since reduction is gaining electrons, and you should always find electrons on the right in oxidation since the electrons are being lost in that process. So the one other thing we need to do before we add these back together is to multiply our coefficients in order to make these two numbers equal to one another. We currently have 2 electrons on the left, 3 electrons on the right. That's no good. So if we multiply this whole reaction through by 3 and our second half reaction through by 2, oops, but I can't do math. Hold on, sorry, I did a bad thing. There were 2 electrons there, times 3 is 6, my bad. There were 3 electrons here, times 2 is 6. So now we have an equal number of electrons on the left and right sides, which will cancel out when we go to add these back together. So we end up with 3 zinc 2 plus reacting with 2 aluminum to form 3 zinc and 2 aluminum 3 plus, which is balanced for both mass and charge. We have 3 zinc atoms on each side, 2 aluminum on each side, total charge of +6 on each side as well.